titration calculations come in endless variations, but they also have certain key sort of things in common. So here's just an example of one, and we'll try to pick out the things that you should always be looking to do as part of your titration calculation. So it might be a good idea to copy this down and have a go at it first, and then come back to the answer once you've had a go at it. Okay, so the first thing is that you've got to be very careful. There are lots of numbers floating around there, and that's commonly the case in these titration questions, and you've got to make sure that you don't get them all sort of muddled up and use the wrong ones in the wrong places. But the starting point should be that there should always be one of the solutions where you know what its volume is and you know what its concentration is. And in that case, that's the sodium carbonate, because it gives you the volume and it gives you the concentration. Okay, so we've got those two numbers for the sodium carbonate, and that's going to be your way in, because if you've got those two numbers you can get moles, and everything then flows from there. So that's our starting point. So we can write down moles of Na2CO3 is concentration times volume in dm cubed, which is 0.100 times 0.025, which is 0.00250 moles. Okay, so that will have been the solution that was in the conical flask, because you've got 25 cm cubed of that, and you were adding the HX solution from the burette, which is why you get a less round number, 27.7 cm cubed for that one. So to relate those two, you need to know the equation, because that's what links moles of one thing to moles of another. So we need our equation, and it's just a standard acid plus carbonate equation. It doesn't matter that you don't know what X is. Just think, well, if it was HCl or if it was HBr or whatever, what would the equation be? And because it tells you it's a group 7 element, so don't let the X's phase you. So we're going to have Na2CO3 plus 2, let's say it was HCl, you'd get 2NaCl plus H2O plus CO2, and then you're saying, yeah, but we don't know it's Cl, so that's just HX, and so we're going to get NaX. Okay, so don't let the X's throw you. So that's our equation, and the important thing about that, the reason we needed it, is that that number tells you that the moles of HX are twice as many as the moles of sodium carbonate. Okay, so the moles of HX in the titration is 2 times the moles of sodium carbonate, and that was the moles of sodium carbonate, so we've got to multiply that by 2, 0.00250 times 2, which is 0.0050 moles. So now we know how many moles of HX were in the titration, but in this titration, as in many titrations, you've got a sort of scaling up step to do, because in the titration you had this volume, 27.7 cm cubed, but that was taken out of a total of 250 cm cubed. And it's the 250 where we know the mass of HX for. So what we need to do is to scale up and say, right, if there were that many moles in 27.7, how many would there have been in 250? So the overwhelming majority of titration questions will have a scaling up step like this. Quite often it's just times 10. If you were scaling up from 25 cm cubed to 250, you just say, oh, well, that's 10 times volume, so that would be 10 times the moles. But here I've just been deliberately awkward and made it more difficult, because you've got to make sure you can deal with these trickier situations. So what you can do, I mean, it may be obvious to you how to scale up, in which case just go ahead and do it, but otherwise think of it like this, that we've got 0.005 moles in 27.7 cm cubed, which means that we'll have 0.005 over 27.7 moles in 1 cm cubed, and we want to know how many there'll be in 250, so it's 0.005 times 250, because if there's that many in 1 cm cubed, there'll be 250 times as many in 250 cm cubed. Moles in 250 cm cubed. Okay, and that comes to 0.04513 moles. Okay, I'm keeping too many significant figures there because that's how you avoid rounding errors along the way. Okay, so that's the scaling up step, that from the equation you get how many moles of HX actually reacted in the titration, but then you think, yeah, but we want to know how many there were in the whole pot, not just the fraction of that reacted in the titration. So we've scaled up from 27.7 to 250. And we did that by thinking, right, if there's that many moles in 27.7, if we divide by 27.7, that's the number of moles in each cm cubed. And then if you multiply by 250, you get the moles in 250 cm cubed, which is what you want. Okay, so where that gets us is here, that in the question it told us that there were 3.65 grams of HX in 250 cm cubed, and now we know how many moles that is, because from the titration we've calculated that there were that many moles of HX in 250 cm cubed. So we can just do this relationship now, that MR is equal to mass over moles, and we know those two numbers for this particular 250 cm cubed, so we can plug those numbers in. So that's equal to 3.65 over 0.04513, and if you calculate that, that comes to 80.9. And now we're almost there, of course, because we can say that the MR of H is 1, and therefore the sorry, that's the AR, not the MR, isn't it? The AR of relative atomic mass of hydrogen is 1, and therefore the AR of X is equal to 80.9 minus 1, which is 79.9. And if you go to your periodic table, that tells you that X is Br. So therefore HX is HBr. Okay, so that's an example of the kind of thing that you can do with titration data. But it's just about being very careful with the numbers at the beginning, making sure that you don't get the numbers muddled up, making sure you notice those things like the need to scale up from how many moles in the experiment to how many moles in the whole pot, and so on. But if you practice lots of these, you come across those things all the time and they become routine, and then these calculations become easy.